Deep inside a nuclear facility in Iran, machines were tearing themselves apart, and no one could explain why. Natanz, Iran. A facility buried under meters of reinforced concrete and desert sand, built to survive an airstrike. Inside, thousands of centrifuges spin at supersonic speed, enriching uranium in near-total silence. This place was designed to be untouchable, sealed off from the internet, guarded by soldiers, hidden from satellites. And yet, in the summer of 2010, engineers here started watching their own machines fail. Centrifuges spun wildly out of control and shredded themselves from the inside. The control room showed nothing wrong. Every gauge, every readout, every alarm said the system was operating normally. It wasn't. Something inside the most isolated computer network on Earth was lying to the humans watching it, and quietly destroying the equipment they were trained to protect. To understand why this mattered, you have to understand what Natanz was, and why the world was watching it so closely. By the mid-2000s, Iran's nuclear program had become one of the most closely monitored geopolitical flashpoints on the planet. Western intelligence agencies, the United Nations, and Israel all believed Iran was pursuing the capability to enrich uranium to weapons-grade levels, a claim Iran denied, insisting its program was for civilian energy. Diplomacy had stalled. Sanctions weren't working fast enough. And privately, according to later reporting, the United States and Israel were exploring an option that didn't involve fighter jets, airstrikes, or a declaration of war at all. Natanz was air-gapped, physically disconnected from the internet, specifically to prevent digital sabotage. Its industrial control systems ran on specialized software from the German company Siemens, controlling programmable logic controllers, or PLCs, the small industrial computers that regulate physical machinery like valves, motors, and, critically, the speed of centrifuges. In theory, a facility like this was unreachable by anything resembling a traditional cyber attack. You cannot hack a computer that isn't connected to anything. That assumption was about to be proven catastrophically wrong. And the story of how it happened would become one of the most consequential in the history of digital conflict, not because of how much damage it caused, but because of what it proved was possible. Consider the stakes on the table. A conventional military strike on Natanz carried enormous risk, retaliation, regional war, civilian casualties, and a level of international condemnation no government wanted to own. Sanctions were slow, and diplomacy had produced years of stalemate. What the world was about to witness, without realizing it at the time, was the quiet emergence of a third option, one that didn't exist in any strategy manual before this. A weapon that could cross a border no soldier could cross, sit inside a facility no spy could reach undetected, and cause the kind of damage normally reserved for airstrikes, without a single missile ever leaving the ground. For years, the people working inside Natanz had no idea any of this was happening. They came to work. They monitored their instruments. They trusted the numbers on their screens, the way anyone trained to operate sensitive machinery is taught to. That trust, ordinary, professional, unremarkable, was about to become the single most important vulnerability in the entire facility. In June 2010, a small Belarusian cybersecurity firm called Virus Blockada was called in to investigate a strange problem. Computers in Iran were crashing and restarting repeatedly for no apparent reason. Digging through the code causing the crashes, researchers found something they had never encountered before: malware using not one, but multiple previously unknown vulnerabilities, so-called zero-day exploits, to spread itself. For context, a typical piece of malware might use one zero-day exploit if the attackers are unusually resourced. This one used four unknown, unpatched vulnerabilities in Microsoft Windows, all bundled into a single piece of malicious code. To put that in perspective, security researchers estimated that even nation-state-level cyberweapons rarely burn more than one zero-day on a single operation, because each one is expensive to discover and instantly becomes worthless once discovered. Whoever built this had access to resources most hacking groups could only dream of. Researchers gave the malware a name, cobbled together from strings found in its code: Stuxnet. Word spread quickly through the tight-knit world of malware researchers. Analysts at major security firms, Symantec and Kaspersky Lab among them, began independently pulling the code apart, and each new discovery seemed to raise the stakes further. This wasn't a hastily written piece of criminal software full of sloppy shortcuts. It was clean, modular, built the way a professional software team builds a commercial product, complete with what appeared to be careful testing, fallback mechanisms, and contingency code for scenarios most attackers wouldn't even think to plan for. At first, nobody understood what it was for. It didn't steal passwords. It didn't steal credit card data. It didn't demand a ransom. It spread aggressively, but oddly, it seemed almost uninterested in most of the computers it infected. It would quietly copy itself, check a few conditions about the system it was on, and if those conditions weren't met, it would essentially do nothing and wait. That restraint was the first clue that this wasn't ordinary malware. Criminal hackers want to infect as many machines as possible and cause visible chaos, fast, because chaos is profitable. Whoever built Stuxnet wanted the opposite. They wanted patience. They wanted precision. And most unsettling of all, they wanted to stay hidden for as long as possible inside a system that, by every rule of cybersecurity at the time, should have been unreachable. Here's the question that stopped researchers cold. If Nathan's wasn't connected to the internet, how did anything get in? The answer forced a rethink of what secure even means. Investigators eventually determined that Stuxnet's likely path into Nathan's was a USB flash drive. Somewhere in the supply chain, a contractor's laptop, an engineer's personal device, a vendor performing maintenance, an infected drive was plugged into a machine that eventually connected, directly or indirectly, to the isolated network inside the facility. Once inside, Stuxnet didn't need the internet anymore. It could spread machine to machine across the internal network on its own, using those zero-day vulnerabilities to jump between computers without a single click required from a human being. Think about what that means for a moment. The most protected facility in one of the most secretive nuclear programs on Earth was compromised not by breaking down a digital wall, but by walking through a door that had been left open by ordinary human behavior, someone using a USB stick. This is the psychological core of nearly every major cyber attack in history, and it's worth sitting with. The strongest technical security in the world can be undone by a single moment of convenience, trust, or carelessness from one person. It's not just Nathan's. It's the accountant who plugs in a drive from a client. It's the employee who charges their phone on an unfamiliar cable. It's you reusing a password because remembering a new one feels like more effort than it's worth. Attackers don't need to break your defenses. They just need you to open the door yourself. And there's a deeper psychological layer here worth pausing on. Human beings are exceptionally bad at fearing invisible threats. We lock our front doors instinctively because a door is something we can picture being kicked in. But a USB drive doesn't look dangerous. It looks like a tool, mundane, familiar, the kind of object you'd hand to a colleague without a second thought. Security researchers have a term for this gap between perceived risk and actual risk. It's the same reason people will refuse to walk down a dark alley but will happily click a link in an email that looks like it came from their bank. The threat that feels abstract is the threat we're worst at defending against. And the people who built Stuxnet appear to have understood that better than the engineers guarding Nathan's did. But knowing how Stuxnet got in was only the beginning of the mystery. The real question, the one that would take security researchers months to answer, was what it was actually built to do once it was inside. Reverse engineering Stuxnet became one of the most painstaking technical investigations in the history of malware analysis. The code was enormous compared to typical malware, reportedly around 0.5 megabyte, built with a level of engineering discipline researchers compared to professional software development, not underground hacking. It was modular. It was self-updating. It had a rootkit component to hide itself, a peer-to-peer update mechanism so infected machines could quietly update each other even without internet access, and forged digital certificates, stolen from real hardware manufacturers, to trick Windows into trusting its malicious drivers as legitimate software. Stolen digital certificates. Let that sink in. To make its files look trustworthy, Whoever built Stuxnet had either stolen or otherwise obtained legitimate cryptographic signing certificates from real technology companies. That's not something a lone hacker pulls off from a bedroom. That takes intelligence gathering capability, or an operation sophisticated enough to compromise the internal systems of hardware manufacturers just to get their digital signatures. And then researchers found the part that changed everything. Buried deep inside the malware was code specifically written to target Siemens industrial control software, the exact systems used to manage the centrifuges at Natanz. Stuxnet wasn't just trying to spread. It was searching, silently, through every machine it infected, for one very specific configuration. A particular Siemens PLC, connected to a particular type of frequency converter, running centrifuges within a very narrow, very specific range of settings. On virtually every computer on Earth, Stuxnet would find nothing matching those conditions, and would sit there, dormant, doing nothing. It was hunting for one target, hidden inside millions of infections worldwide, the way a predator might move silently through a crowd searching for a single, specific face. By some estimates reported at the time, Stuxnet spread to well over 100,000 computers across dozens of countries. Factories, offices, personal machines, most of them with absolutely no connection to nuclear enrichment at all. Reports at the time noted infections detected in India, Indonesia, and elsewhere, largely as unintended collateral spread rather than deliberate targets. Picture that scale for a moment. A weapon built with the precision to identify one specific industrial configuration, deliberately released into the wild in a way that let it wash across the globe like static, silent on every machine except the one it was actually built to find. That combination of massive reach and near-surgical restraint was, to researchers at the time, almost a contradiction. Nothing behaved like that. Nothing had ever needed to. It took teams of analysts, working for months, cross-referencing disassembled code against industrial engineering manuals most of them had never had reason to read before, to finally understand what they were looking at. Some of the researchers involved later described the process as less like fighting malware and more like defusing a bomb built by someone who had never wanted it found in the first place. When Stuxnet finally found its target, what it did next was almost theatrical in its cruelty. It didn't crash the system. It didn't trigger an obvious alarm. Instead, it quietly took control of the centrifuge's speed, forcing them to spin far faster than their design tolerance for a period of time, then abruptly slow them to dangerously low speeds, cycles of stress engineered to physically wear down and destroy the delicate, high-speed machinery from the inside, over weeks and months, in a way that could easily be mistaken for manufacturing defects or operator error. And here is the detail that made security researchers around the world go quiet when they finally understood it. While Stuxnet was doing this, it simultaneously fed the plant's monitoring systems pre-recorded, normal-looking data, a digital forgery of the centrifuges behaving exactly as expected, playing on a loop for the human engineers watching their screens. It was the industrial equivalent of a security guard being shown a looped video feed of an empty hallway while the actual room behind him is being ransacked. The engineers at Natanz weren't just being sabotaged. They were being deceived in real time by their own instruments, trained their entire careers to trust the numbers on the screen, and those numbers were lying to their faces. This is the same psychological exploit behind nearly every successful scam and manipulation. We trust the interface, the readout, the caller ID, the verified checkmark, not the underlying reality. Stuxnet weaponized that trust at an industrial scale. Estimates on the damage vary, but reporting citing nuclear analysts and former IAEA officials suggested Stuxnet may have destroyed close to 1,000 centrifuges at Natanz and set Iran's uranium enrichment efforts back by a period some analysts estimated at 1 to 2 years, all without a single explosion, a single soldier crossing a border, or a single official acknowledgement from any government that anything had happened at all. Picture the engineers on shift during those months. Alarms staying silent, readouts staying calm, and somewhere beneath the floor, machinery spinning itself apart in a rhythm too subtle, too gradual, to register as an attack. Later analysis suggested the malware was even designed to record around 30 seconds of legitimate sensor data during normal operation, then loop that recording back to the control room for the duration of the attack, a detail that, once understood, reads less like a piece of software and more like a hostage tape, forcing the system's own past to lie about its present. There's a reason this detail resonates so deeply beyond the world of industrial engineering. We live now inside a constant stream of dashboards and readouts of our own, bank balances, delivery trackers, security camera feeds on our phones, last seen online, timestamps, two-factor confirmation codes. Every one of them asks for the exact same kind of blind trust the engineers at Nathan's placed in their monitoring systems. Stuxnet is a reminder that an interface is not the same thing as reality. It is simply the last place a sufficiently capable attacker needs to lie to you. Even a weapon this disciplined left traces behind. Buried in Stuxnet's code, researchers found small, almost careless details that hinted at its origin, the kind of thing that happens when a team works quickly under pressure, or simply doesn't expect anyone to ever read the code closely enough to notice. One file inside the malware contained the string Murtis, which some analysts speculated could be a reference to the Book of Esther, a story in Jewish scripture involving a foiled plot against the Persian Empire, a connection researchers flagged as intriguing but circumstantial, not proof. Elsewhere, researchers found a date value embedded in part of the code, 197900509, formatted as a date, May 9, 1979, the day an Iranian Jewish businessman named Habib Elghanian was executed in Tehran following the Iranian Revolution, an event with deep resonance in Israeli political memory. Again, suggestive, not conclusive. Digital breadcrumbs like these are notoriously easy to misread, and sophisticated intelligence operations have been known to plant false clues specifically to mislead investigators chasing attribution. What tipped the scales for many researchers wasn't a single clue, it was the accumulation of everything together. The zero-day arsenal, the stolen certificates, the intimate, specific knowledge of Siemens industrial hardware used almost exclusively in enrichment facilities like Nathan's, the restraint, the patience, the total absence of any criminal motive like theft or ransom. Every thread pointed the same direction. This was state-level work, built by people with access to intelligence most private citizens will never see, aimed at a target most private hacking groups would have no conceivable reason to care about. Here is the twist that turns Stuxnet from a fascinating piece of malware into a geopolitical event. This almost certainly wasn't the work of criminals, or hacktivists, or even a rogue individual state actor showing off. Multiple investigative reports, most notably from the New York Times in 2012, citing anonymous current and former American officials, described Stuxnet as part of a covert program reportedly codenamed Olympic Games, said to have been initiated under the Bush administration and continued and expanded under the Obama administration, developed as a joint operation reportedly involving American and Israeli intelligence and military cyber capabilities. No government has ever officially, formally confirmed this in full detail. But the circumstantial case, built by researchers and journalists over years, is extraordinarily strong. The level of intelligence required to know the exact model of centrifuges at Nathan's, their precise operational tolerances, and the specific industrial control configuration in use, that is not information available on the open internet. That is the kind of specificity that typically requires human intelligence on the ground, or access to classified engineering data, feeding directly into weapon design. This is why Stuxnet is widely regarded by cybersecurity historians as the first publicly confirmed cyberweapon used to cause deliberate physical destruction to critical infrastructure. Not theft, not espionage, not disruption. Physical, mechanical destruction of a nation's strategic assets, executed entirely through code, allegedly by other nation-states, with no formal declaration of war, no attributable soldier, and, for years, no public acknowledgement at all. Researcher Ralph Langner, one of the first independent analysts to publicly piece together what Stuxnet's true target and purpose was, became one of the most prominent voices explaining its significance, describing it in various public talks and writings as a fundamentally new category of weapon, one built not to spy, but to destroy something physical using nothing but software. Think about the precedent that sets. If a piece of code can quietly and deniably cripple a nuclear facility, what stops the same logic from being applied to a power grid? A water treatment plant? A hospital's oxygen supply systems? Stuxnet didn't just damage centrifuges. It demonstrated, to every government watching, that critical infrastructure anywhere in the world was now a viable battlefield, and that the weapons for that battlefield could be built in a lab instead of a factory, and fired without ever crossing a border. There's also something worth sitting with about the decision to release a weapon this contained into the wild at all, even if the spread beyond Nathan's was reportedly unintentional, caused by a later variant that behaved more aggressively than intended. A tool built with this much surgical precision escaping its intended boundary is, in itself, a kind of warning. Weapons built for war rooms don't always stay in war rooms. Once code exists, it can be studied, copied, and repurposed by other states, by criminal groups, by anyone with the patience to reverse engineer it. Several of the same zero-day vulnerabilities and techniques Stuxnet relied on were later observed, in modified form, in unrelated attacks years afterward. A weapon this precise was still, in the end, a weapon that got loose. Once Stuxnet was exposed, the fallout unfolded in layers. Iran publicly acknowledged in 2010 that a piece of malware had affected personal computers of staff at its nuclear facilities, while downplaying its impact on the nuclear program itself. Independent nuclear monitoring data, however, including reports referencing statistics from the International Atomic Energy Agency around that period, appeared to show a drop in the number of operational centrifuges at Nathan's consistent with the kind of covert sabotage researchers had described. For the cybersecurity industry, Stuxnet triggered a fundamental shift. Before 2010, industrial control systems, the software running power plants, water systems, and manufacturing, were treated as a niche, largely ignored corner of security research, protected mostly by the assumption that they were too obscure and too disconnected to be worth attacking. After Stuxnet, an entire new subfield of cybersecurity emerged almost overnight, dedicated specifically to defending critical infrastructure and industrial control systems, because researchers now had definitive proof that these systems could be reached, understood, and destroyed remotely. For nation-states, the message was different and arguably more dangerous. Stuxnet proved that cyberweapons worked. It proved they could achieve strategic military objectives with plausible deniability, without risking soldiers, without a formal declaration of war, and largely without international legal consequence, because international law had no real framework for classifying or responding to this kind of attack. In the years that followed, cybersecurity researchers and intelligence agencies around the world documented a wave of increasingly sophisticated state-linked malware campaigns, many showing design philosophies, tools, or targeting patterns that researchers believed were connected to or inspired by the same operators or techniques associated with Stuxnet, including malware later dubbed Doku and Flame, which were widely assessed by researchers to share code architecture with Stuxnet, though used primarily for espionage rather than physical destruction. No one has ever been formally charged or convicted in connection with the creation of Stuxnet. No government has fully claimed responsibility. To this day, it remains one of the most consequential unattributed attacks in the modern era. A weapon that changed the rules of international conflict, launched by no one on the record. The diplomatic consequences unfolded slowly and mostly out of public view. Iran's negotiating posture in later nuclear talks was shaped, at least in part, by an adversary that had proven it could reach places assumed to be untouchable. Meanwhile, in defense ministries and intelligence agencies far beyond Washington, Tel Aviv, and Tehran, Stuxnet became required reading. Military planners in countries with no direct stake in Iran's nuclear program studied the case anyway, because the real lesson wasn't about centrifuges. It was about doctrine. A precedent had been set for what an acceptable, deniable, non-kinetic first strike against another nation's infrastructure could look like. And once one government demonstrates a capability like that works, others tend to want it too. By the middle of the decade, multiple governments, including the United States, Russia, China, Iran itself, North Korea, and others, were widely reported by researchers and journalists to be building out dedicated offensive cyber units, explicitly citing infrastructure and industrial targets as part of their mission. Stuxnet didn't invent state-sponsored hacking, but it proved a specific, terrifying subcategory of it was viable at scale. Hacking that reaches out of the screen and breaks something in the physical world.